Okay, this is three-wire circuits part 2. So what I've drawn on the board here is I've drawn a three-wire circuit that has two 120 volt connected loads and a 240 volt connected load. Now, what we learned in the previous video was the differences between balanced and unbalanced. And I'd ask you this, in looking at the current values that I've asked, or that I've said that these loads are going to draw, would this be a balanced or unbalanced circuit? The answer would be an unbalanced three-wire circuit. And we know that because line 1 load, line 1 to neutral, requires 6 amps, but my line 2 to neutral requires 12 amps. So that tells me that I have to have current on my neutral. All right? How can I come up with how much? We can analyze what's happening out here. We could go the 10 plus the 6, giving me 16 amps leaving there. The 10 plus the 12, having 22 amps returning back. Okay? The difference between the 22 and the 16 is going to be 6 amps. Whatever leaves has to come back, so if we had 22 returning, we have to have 22 leaving. All right? So, in this circumstance, with the unbalanced neutral, okay, if there was, all our connections were good, this is the worst case scenario, or I guess the best case scenario you could say. However, if we made a mistake and did a bad splice in here, we need to analyze what effect that would have on this circuit. Now keep in mind, that connection there, or that misconnection there I should say, does not have any effect to what's going on out here at my 10 amp load. Okay, that 240 volt load is unaffected by this. We're only going to deal with what's happening inside here. Alright, so if I come over here and redraw this, simply to focus on those lighting loads, okay, I'm going to get rid of the neutral for the time being because we know we only have a 240 volt source, okay, because we've lost the neutral. So we've got line 1 to line 2 potential, all right? The first thing that I need to do to be able to solve for this would be to solve for the resistance of these loads before they broke. So in other words, we're going to look at the voltage at each of these before the break, which would have been 120 volts and 120 volts, okay? And we're going to divide that by our 6 amps and our 12 amps, okay? So if I do that, that's going to give me a value of resistance for each of these guys. So 120 divided by 6 is going to give me 20 ohms. And 120 divided by 12 is going to give me 10 ohms. Okay? So I've got 20 ohms here and 10 ohms there. Alright? Those are series connected to the 240 volt source. If I divide that R total, which is the 20 plus the 10, giving me 30, into the 240 volts, I can get my new circuit current for that portion. Okay? And you can go 240 divided by 30, that should come up with 8 amps. Alright? So now we have 8 amps flowing on that portion. Not the 6 and the 12 that were there originally. Alright? Using that current and the original resistances, we can solve for voltage drops. So 8 times 20 gives me 160 volts, and 8 times 10 gives me 80 volts. Now I know in the previous discussion, the values for those loads came out to the exact same thing here. Okay, it's not always going to be the case. This is just the way that this circuit has worked out. All right? So, if we bring these values back over here, the changed current values are no longer going to be the 6 and the 12. That's still drawing 10, okay? But we know we have 8 amps there and 8 amps here still, okay? So 8 plus the 10 gives me a new line current up here of 18 amps. And whatever leaves has to come back, so the 8 plus the 10 gives me another 18 amps there. No current on the neutral because it doesn't have an ability to flow because of our bad splicing, okay? And then ultimately we're always going to ask you, what is the voltage or the potential difference across that break? Okay? So, if you remembered what I did in the previous lesson, we would go 120 volts minus 160 volts, or the other way around. That'll come up with 40 volts. I know that's a negative, but it's got a 40 volt potential. And then the difference between this point and this point, from this to this, that's the 80 volts down there. Okay, 120 minus 80, okay, would give you the 40 volts as well. You can either do the top or the bottom. The value should be exactly the same or very near the same if you've got some rounding of numbers going on, okay? So you got a 40 volt potential difference between those 2 points. You've got one load drawing more current than it was rated for and having a greater voltage drop than it was ever rated for, okay? Meaning it's probably going to fail. Or the other way around, let's say this is your refrigerator, okay? If you feed your refrigerator with only 80 volts of supply to it, it's going to be really, really hard on the equipment to try to operate. So your refrigerator might fail, okay? So open neutral circumstances due to poor splicing is a real problem within our installations, okay? So whenever we're making our connections within the junction boxes of our devices, we need to make sure that we're doing proper splicing to ensure that we do not have this problem created, okay? The next video we'll talk about what happens if we had a balanced or an unbalanced circuit, but then we lost one of the line conductors and the results of that, okay?